This is the first section of our probability chapter. We're going to be looking at random experiments and sample space. Our first three terms are chances, probability, and odds. And sometimes these get confused with one another. They sound kind of similar, but mathematically they're actually different things. So when we talk about the chances of something, we typically use percentages. So the chance of rain tomorrow is 40%, for example. With probability, we would say favorable outcome out of the total possible outcomes. So, and the equivalent for 40% would be 2 out of 5, so 2/5. And then with odds, you say favorable outcomes to unfavorable outcomes. So, and you write it as a ratio with the colon in the middle. So, the odds of the Red Sox winning the World Series are 2 to 3. And notice here that's 5 total outcomes, so 2 and 3 make 5, so that would be 2 out of 5, which is another way to write 40%. A random experiment describes an activity or process whose outcome cannot be predicted ahead of time. And the sample space, usually associated with random experiments, is the set of all of its possible outcomes, so everything that could happen in an experiment. We're going to use the letter S to denote a sample space and N to denote its size, so the number of all possible outcomes within that sample space S. So some examples of sample space, flipping one coin, we could get heads or tails, and that's it. If we flip 2 coins, and if we care about the order of which it happens, so heads then heads, heads then tails, or tails then heads, and then tails tails. So that will give us 4 possible outcomes in the sample space. Rolling 1 die, so we get a 1 through 6. Rolling 2 die, we get a 2 through 12. Remember that from rolling 2 die, it's impossible for me to get a sum of 1. In this example, let's pretend your favorite basketball team is down by 1 when one of the players gets fouled. He goes to the free throw line to win the game, or to try to win the game. What is the sample space of the 2 shots? Well, the first shot, he can either make it or miss it. So for making the shot, we'll just say yes, and for not making the shot, we'll just use no. So our sample space would look kind of like this. So S is denoted by yes for the first shot, and then maybe yes the second shot, which would win the game. We could also have yes for the first shot, no for the second shot, tying the game. Another scenario where you would tie the game would be not making the first shot, but making the second shot. And then if he makes neither shot, we would lose the game. So those are all 4 scenarios here. Next, what is the sample space if the second shot relied on a successful first shot? So a lot of the times in a basketball game, depending on the number of fouls that the other team has committed, you may be awarded a 1-and-1 shot where you have to make the first shot to be awarded a second free throw. So our sample space for this scenario would look like this. We'd have first making the first shot and then maybe making the second shot. So yes, yes. We could also have yes and then missing the second shot. And then the last thing that could happen is just missing the first shot and then not being awarded a second shot. So those are the 3 scenarios or the 3 outcomes that are possible. Lastly, what are the ends? This basically is asking what are the sizes of each sample space. So for this first example, there are 4 outcomes, so we would just say n equals 4. And then for our second example, where the second shot relied on a successful first shot, we would say n equals 3. Another example here, rolling dice. This is a very common thing that we can relate to probability. So usually when we roll a pair of dice, we're just concerned with the total number that it lands up on, but we're going to treat these dice as separate things, so we're actually going to list out all 36 different outcomes. So notice the first one is a 1 and a 1, then we have a 1 and a 2, we can get a 1 and a 3, and this goes all the way up to the possibility of rolling a 6 and a 6 to create a sum of 12. You may have already noticed below that there's a couple outcomes that look like they're just duplicates of each other, but if we treat the dice as distinguishable objects, they're actually different outcomes. So we could get a 5 and a 2, or a 2 and a 5 to make 7. And this is actually really important because the chances of rolling a 1 are very different from the chances of rolling a 7. Look down at the bottom where we have all 36 outcomes. There's only one way we can get a 2, and that's right here with a 1 and a 1. But if I want to roll a 7, a 5 and a 2, we can get, let me find that on here. Okay, so a 5 and a 2, we could get a 2 and a 5. We could get a 3 and a 4. We could get a 4 and a 3. We could do 1 and 6. Could do 6 and 1. So there's actually a lot more ways to roll a 7 than there are a 2, and that's important to take into account when you're finding the probability of these events. Another example here, 4 candidates A, B, C, and D running in an election. The top 3 vote getters are chosen president, vice president, and secretary in that order. What is the sample space? So this one's going to have a lot of answers. The best thing you can do when you get a problem like this where you have to think of, okay, how many combinations or how many different ways are there for me to order candidates, is to organize it somehow or to draw some kind of picture. So I'm going to make kind of like a tree here. So for example, we could have candidate A, we could have candidate B, candidate C, and candidate D. So let's say that candidate A gets the most votes. Okay. Then it can be, after A, it can be B, C, and D. And then from there, so we could have A getting first, B getting second, and then from B, we could have either C or D. From C, we could have either B or D. And from D, it could be either B or C after that. So in the end, and there's 4 of them, but we're choosing 3, so we would have A, B, and C as the winners, so that combination would look like A, B, C. The next combination would look like A, B, D. Okay. The next combination would be A, C, B. Then we could have A, C, D. And then A, D, B. And lastly, A, D, C. Okay, and those are just all the combinations, really I should say permutations, and we'll get into that later where we talk about whether or not order matters. But so these are all the possibilities where A is the top runner and everyone else follows. So, and I'm not going to finish this because it'll take a little while, but tree diagrams are always great when we're listing out all the possibilities. So you would just finish this one for B, C, and D to list out the entire sample space for the problem. In this example, we roll a regular 6-sided die twice and note whether it lands on an even number or an odd number on each roll. What is the sample space for this random experiment? So we can either have the first roll be even, the second roll be even. We could have the first roll be even and the second roll be odd. We could have odd and then even, or both odd, similar to the heads and tails example. So our sample the size of our sample space here would be 4 outcomes.